Right, thank you very much, Carl. Can people see this red dot? It's not very large. Can you kind of see that at the back? Okay, good. So yeah, I'm going to be talking about this thing called Bayesian optimization. I've got lots of pictures. We're going to revisit the same thing several times from different perspectives. So if you're not quite on top of things early on, don't worry. You might come good later on. Please do ask lots of questions whenever you feel like it. But just to start and motivate this problem, we're going to think about something a little bit more broad. So an idea about Bayesian search. So we're going to motivate this with a silly sort of toy problem. And we're going to be interested in finding Carl-Henric on one of his fantastic journeys. And we're going to try and be a little bit more clever about how we do this. Okay, so this is a bike ride that Carl did last year. So he started in Paris, and he rode all the way out to the edge here, to Brest, and all the way back again. How long did it take, Carl? 79 hours. And we're going to imagine that we were a bit worried about his whereabouts, which is a completely valid state of being to be in, I think, with Carl. There's a picture of Carl on a bike ride, in quite good shape here. He's only sitting on the floor. Sometimes worse things happen. And yeah. But this isn't this ride, though, Carl. No. 70 hours wouldn't get you into this state, I guess. This is a longer event. Yeah. Okay, cool. Okay, so we're interested in working out where is Carl-Henric at 3:30 a.m. Okay, it's a very, very valid question, good question to have. And we've kind of got this sort of understanding of how the system is going to work. We know the distance that he's going to travel is just going to be his speeds times how long he's been cycling for. So up front, we're going to have some sort of prior over what's going on. We're going to parameterize the velocity. So that's the thing that we don't really know. We don't know how fast he's going. We don't know how good he's feeling, how much milk he's drank, this sort of thing. So we've got a lot of uncertainty going on here. But the idea is, can we kind of make some measurements to work out where he is and over time improve our understanding? So this is kind of a Bayesian search problem here. So what we might do is just randomly pick a place. So we'll pick a place and a time. Sorry, we pick a place here. And we say, have you seen Carl-Henric? So we phone up the people in the village here. And they say, yes, we saw him at 12 p.m. Okay. So then we have some information now which is going to update our prior about where we think Carl-Henric might be. So we see we've gone from here to here. So we know that he's going faster than a certain speed, right? He's made it at least this far in that amount of time. Okay. So we've kind of collected a bit more data, and we've learned more information about the thing we care about. We might make another measurement. We might phone up some guys over here, and they say, no, we haven't seen him. Okay. So that gives us an upper limit for where he's been. And so on and so forth. We can just be kind of randomly choosing locations. And over time, we're going to get a more and more accurate estimate of where he is. And so this is kind of illustrative of the sort of methods that we're going to be interested in this talk. So we have some sort of model. This is a very simple model just to motivate things. Nothing very exciting here. We're going to be talking about using Gaussian process models. And we're going to be designing experiments to kind of reduce uncertainty about key properties of a system. So it turns out we can find him here. So this is from the tracker on the website. Me and one of my master students, we spent most of our supervision meetings last year logged into this website and seeing where he got to each day. But yeah. But anyway, yeah. But the entire motivation for all of this sort of work, this sort of active learning or Bayesian optimization, Bayesian search, all of these things is about coming up with some clever strategy of using a model to drive some sort of data acquisition. So perhaps a slightly more specific example now, but still a bit more broad than Bayesian optimization. We have this thing called active learning. Okay, so has anyone here used any sort of active learning before? Yeah, okay, nice. Quite a few people. Cool. But do interrupt if I say something wrong. But the entire point here is that we're interested in collecting data, but in a sequential way. Okay, so this is a picture of what's going on. So we have some initial data set that's been given to us, typically. You know, we've downloaded it, or some scientist has gone and collected it in the lab. And then we have a pipeline that looks a bit like as follows. So we'll fit an initial model, a machine learning model or a statistical model to that data. And then we'll have a bit of a think. Let's collect some more data. So we have a particular property we're interested in. Maybe we're interested in where is Carl-Henric. Maybe we're interested in, you know, what should the length scale of my Gaussian process be, or my ability to make kind of good predictions. And I'm going to use that property to determine what extra data I should collect. And you might do this several times. So each time you fit a model, you look at the model, work out where its weaknesses are, and collect more data to kind of help with that. And you do this many times in a sequential way. So this is a sequential data collection pipeline, an active learning pipeline, if you want. And the idea is that you finish with this final model that's going to be much better for the thing that we're interested in than this initial model you had, right? You've collected lots of very relevant data. You've got a very customized model that's going to be really good. So just a really stupid picture example again here. Imagine there's some sort of underlying process, this black wiggly line. I don't know what this is, okay, but I'm going to try and learn this from some data. So what we might do is randomly collect 10 data points. We fit the Gaussian process. So this is your sausage plot. I know Carl doesn't like, did you go on about not liking sausage plots? Okay. This is packed full of sausage plots, this, yeah. Oh, you did as well? Oh, okay, yeah. I also don't like them, but I couldn't be asked to make my slides again. But I think it makes sense for this sort of context a little bit. But yeah, they are very misleading, these sausage plots. But this is what we're going with here. So yeah, we've got a mean prediction, the dark blue line, we've got some uncertainty. Okay. What we might then do is collect a bit more data. So I've collected another random 10 data points, and you see that we're whittling away at the uncertainty. So we're getting a better model. These models are all quite good. They seem quite well calibrated. Like the line is kind of within a lot of the mass here. And then we might collect a further 10 random data points. Okay. So you see over time, we're getting a much better model. We're really learning our process here. This is all random. And of course, we could do something much more interesting than random. So for this particular problem, where all I'm interested in doing is pinning down this wiggly function, there's a quite simple strategy that would work well here. Does anyone know what that might be? If I wanted to say I'm here, and I need to choose 10 more data points to collect, what would you do? Yeah.
Pick points where the uncertainty is largest.
Yeah, exactly. So you basically try and go into the largest uncertainty, which is equivalent for a Gaussian process with a standard kernel to just going like the furthest away from data you've already seen. So when your goal is just kind of getting a model that's got the best predictive performance over your input space, there are some quite simple strategies you can use. So just a few more examples here. So this is the problem I've just described there. So if we're interested in a regression problem, and we have a regression model, we have the chance to collect a bit more data. Let's collect the data so that it gives us the biggest kind of improvement in predictive performance. This is the thing we're going to focus on in this talk. But if we care about, this sounds very specific at this point, but hopefully it'll become a bit more kind of useful towards the end. But if I care about learning what is the maximum value of the process, so this isn't learning everything about the process, this is just learning one very particular property of the process. Then there are methods you can use, which are methods like Bayesian optimization, which allow you to kind of very efficiently find this maximum value by focusing data acquisition in the right places. But we're going to focus on this for the rest of this talk. Another interesting part of this is if you're interested in, say you've got a few different processes and you're interested in areas of the search space that correspond to high-scoring regions for multiple objectives. We'll go into this a little bit as well. Don't worry if this makes no sense whatsoever at the moment. And then another example, which is kind of more similar to, I guess, a more traditional active learning setting, which I'm not going to talk about, but I thought it was useful to kind of motivate, is if I'm interested in, say, learning a threshold. So a good example of this might be, this is kind of a standard toy data set in active learning. You're interested in basically trying to predict this binary classification task. So this is, if it's yellow, there's a malaria incidence above a certain threshold, and purple is below. And if you just collect random data points, and then you fit a model, so here I think I fit a Gaussian process classification model, you see that you kind of, it's not great, you get some of the features, but then if you're very clever and you kind of use an active learning method to focus your data points, you could collect a data set where you get a really good model of the threshold. So you see you're focusing the data a lot on these sort of boundary regions and not bothering in these areas where you kind of know what's going on. But yeah, Bayesian optimization. Okay, so I'm going to try and motivate all of this first section in terms of a molecule design problem. So this is a slightly atypical way, I guess, to present Bayesian optimization, but it's quite visual. And then we're going to come back to kind of the more standard setting where you have a continuous input space and we can write down more of the maths and things. But at this point, this is going to be largely just a visual demonstration that will hopefully get people thinking. So let's think about what these sort of pipelines look like. So maybe you're a scientist working for a pharmaceutical company and you have a ginormous library of molecules that you have stored somewhere in the company, which are the molecules that you know how to make. And you want to basically very quickly explore this large set of molecules. So you want to find a molecule that has a particular property, but you have a very kind of, in the context of the large number of molecules you have available, you can only evaluate a small number of these. So every time you want to see if a molecule is good for a particular task, you have to send it off to the laboratory, right? So it could be like a day of time, someone's got to work on it, it's going to be expensive for all the materials. So maybe you only get like 10 chances to collect more data in this setting. There's also an interesting aspect to these problems, typically where you have a very high degree of parallelism. So fine, I can only make 10 sort of sequential data collection steps, but at each of these steps, maybe I can collect 1,000 or 10,000 measurements. So if you're going to do one of these lab experiments, often it sort of costs the same to do a whole array of molecules, so a big batched experiment in the lab, as it does to just do a single one. So basically, you're kind of in this setting where you have a model up front, you're going to pick, say, 1,000 molecules, they're going to go do some experiments, come back, and then using all of that information, you're going to pick some more. Okay, so the idea is, can you efficiently explore this very large space? And then there's always some objective here, so we're interested in molecules that, for example, might have a high affinity, or just you can think of any property here. But typically, there's a few things going on. So it's never just a single objective here. We're interested in finding molecules that are good at something, but that are also easy to make, whatever that might mean. They also, they don't stick to themselves, so that means they're quite stable. So they have a nice long shelf life, for example. If you're going to bother to make these into a drug, you need to be able to leave them in a shop for a while. And there might be other constraints to do with kind of legal requirements. But yeah, this is kind of a really complicated problem, I would say. Does anyone have any ideas about how you would go about this? I guess this is quite a hard question. Yeah, but this is kind of, we're going to go through the motions of this now. But basically, Bayesian optimization is a really good way to deal with this problem. And hopefully I'll motivate, hopefully I'll justify that as we go. Oh, I don't know what's going on there. Okay, cool. So let's look at a much simpler example here where we have 6 molecules available to us. These 6 molecules, and our total evaluation budget is 4 molecules. Okay, which 4 of these would you pick? Can someone give me an idea and a justification? This is also quite a hard question, perhaps, for a last day of the summer school in the morning. Yeah. Oh. And what would that look like for this? Perfect, that's great. Yeah, normally no one can answer this question, so that's good. It feels like I've placed you in the middle there. And that's really good. So I think that's a much more eloquent description. Basically, I've kind of said the same thing here. I'm breaking them up, but again, without the nice scientific justification, but it's the same sort of idea here. The idea is, can I somehow break these up into kind of clusters in a way? And that's what you're describing. And this would be kind of an interesting thing to do. So I said I'm allowed to evaluate 4 of these molecules. So something that's quite natural to do is to spend the first 3 of those evaluations. Oh, has this suddenly gone really weird? Okay. Doing something like this. So here I'm kind of grouping these guys. I mean, so this is like my noddy understanding of science. I'm like looking at these things, and I think these ones look a bit more similar. Perhaps, I don't know. But I'm not going to ask you about this. And these guys look a little bit more similar, and these are a bit more similar. Okay, so this isn't actually what we do. We normally have actual scientists that do this sort of thing. But at a very high level, you can imagine this seems like quite a reasonable thing to do. Basically, if I evaluate one of the molecules from these 3 sets, each, I can get kind of an understanding for the whole of this space to some extent. And then, yeah, and then my final step would be to kind of pick one of these guys, maybe the one. If I've evaluated the top molecule from each of these buckets, and then one of these buckets has a really good score, it would make sense to then evaluate the other one in that bucket. Okay, so that would be kind of quite an interesting strategy that I would go for. And that kind of encapsulates this core idea that's common for all of the Bayesian optimization stuff I'm going to talk about. When anyone tells you anything about Bayesian optimization, you should be thinking, is there some exploration aspect to this or an exploitation aspect? So this initial part here where we're saying, okay, we want to have an efficient coverage of the whole of the space so that we have a good model, that's known as exploration. So I'm just exploring the space, trying to work out which areas of molecule space are worth exploring, worth evaluating. And then there's this step where we've suddenly changed what we're doing now, where we're going, okay, we've got one last evaluation, let's really double down on an area we think looks promising. So that's known as exploitation. Okay, right? It could, I mean, this is a toy, silly example, but it could be kind of anything to do with the molecule, maybe stability of the molecule, or its ability to bind with a particular target, or yeah. Yeah, they have proxies. Like, this is really, really on in the molecule, or in the drug design pipeline, right? This is kind of almost R&D at this point. It's far away from actually building drugs that go into people. So the objective here is never actually, has it cured someone? It's always, the scientists have an idea about some things they're interested in, some kind of indicators like we described here. But there's a whole bunch of objectives typically. So yeah. And the idea is, often you're not really interested in ever finding a single molecule. You want to find a large collection of good molecules that are in some way distinct, typically. But yeah. So this sort of notion of exploration and exploitation, yeah, central to all of the stuff that we're gonna talk about. Okay, so we've kind of spent a lot of time now just sort of talking about these 6, right? So we can eyeball this, we can make interesting decisions. Manually, we can have arguments about this all day if we wanted to. But as soon as we go into a setting where there's lots of molecules, so this is a few more molecules, but yeah, you might have millions, perhaps billions of these molecules in your sort of candidate set. So you need some way that allows you to scale up these sort of arguments. Right? If I'm going to choose, 1,000 molecules for each step of my data acquisition, I can't be sat there manually picking things. So the entire point is, can we essentially automate this sort of these sort of heuristics that we were implementing on the previous slide? And it turns out you can. You have to use Gaussian processes. Well, that's one way of doing it anyway. And yeah, this is a very popular method. So just a quick aside. So we're talking a lot here about models over molecules. Okay, so we've spoken a lot about Gaussian processes where you have continuous inputs. Okay, you can have all these nice sausage plots. In this setting, what I'm doing is I want a model that's going to kind of predict a property of a molecule. Okay, so my input here is going to be a molecule. I've made this sort of cartoon subscript I here to denote the ith molecule. So my data set here is going to be, I'm going to have n molecules and then n measurements of each of those molecules. And a measurement here would be the property I'm interested in, calculated in the lab, modulo a little bit of noise, typically a bit of experimental noise. Okay. So what do we need if we want to define a Gaussian process? That's the question. A kernel, right. So that's the main thing. You need a mean function as well, but you can kind of ignore that a little bit. But certainly, yeah, a kernel function. So you need some way of essentially measuring similarity between two molecules. And that's something that's quite powerful about these Gaussian process models, is that that's all you need, right? If you wanted to build a neural network model of molecules, you'd have to work out a nice, clever way of featureizing the molecule, working out what features are important and feeding them in. In Gaussian process, or kind of kernel methods more broadly, all you need is this notion of a kernel. So if you can kind of think, or you sort of eyeball these things and you sort of think of a way that you might measure similarity between them, you're probably in quite a good place. So I've got 2 examples here. The details here aren't super important. I just thought I'd kind of have it in if anyone was interested. But one way you might define similarity between 2 molecules is through things called fingerprint kernels. So these fingerprint representations of molecules have been around for a very long time from the chemical informatics literature, very well motivated, and they're very powerful as well. So the way this works is that we basically just have a way of featureizing these molecules, but in a non-data driven way here. This is just a representation. So what you do is, so if you had a molecule like this, for example, what you'd be interested in doing is looking at all the unique kind of substructures within this molecule up to a certain sort of size. So here we're looking at, say, up to 3 here. So we'd be interested in any structure like this one, like that, for example. And what I do is I have a very long vector that's told me whether or not these structures are in my molecule. And this would be a ginormous vector. So typically you kind of hash it just to do a dimensionality reduction, and you end up with a binary vector, maybe with 1,000 elements or 2,000 elements, something like that. And that's just a nice way of representing these molecules. And then you've got these long vectors, so you can just define a kind of a standard GP kernel for this. Does anyone know why I would use a linear kernel here rather than like an RBF kernel, for example? Maybe you haven't talked too much about linear kernels. So this is a very high-dimensional input, right? So these RBF kernels typically are very flexible models, and they perform quite poorly, unless you set them up very carefully, for high-dimensional problems. I'm happy to talk about this afterwards, because this is like the first thing that happens. People come to these sort of talks, they go away, they fit an RBF kernel to like 10, even just 10-dimensional data set, and weird things happen, basically. So you've got to be a little bit careful in this like moderate dimension. This is certainly a high-dimensional problem, but you have to use the right sort of kernels. It's not true that GPs are bad in high dimensions. It's just that the kernels we use are often. Yeah, does someone have a question?
I was just going to say, like, you sort of mentioned anyway about having too many hyperparameters because your vector is so long, but also, there's an aspect of you need more data to make up for it.
Yeah.
Hyperparameters, obviously, your data set is limited, so, you can't scale the number of inputs with the number of hyperparameters, basically.
Yeah, so it's this like curse of dimensionality, like typical setting, and you get that for like an RBF kernel, a stationary kernel like that. There's some interesting results where you need kind of to be able to pin down a function to the same level as you increase the dimensionality of your problem. The underlying function would have to have length scales increasing at like this, like a root dimension sort of rate, and that's not what you get when you fit these models typically. So you need if you want to learn, say, a RBF kernel over a very high dimensional input, the function would have to be incredibly smooth, essentially, for this reason. Yeah.
One other question. What do you use to hash the vector?
Yeah, so just push it through like a hashing function, like a random function that just compresses things down.
Like a string?
Well, just to get, well, it's in the context of like a bit vector, so it's a hashing function to a bit vector. But kind of a similar idea, yeah. You're just kind of getting rid of a load of redundant information, hopefully. Yeah. Yes? You're using the same hashing function for all the molecules. So there is some sort of information. It's like called the hashing trick. It's something that exists in machine learning for like information compression. But it's kind of, it's not super principled, but it's very effective. And it works well for these because you are very sparse. These vectors are incredibly sparse, right? Like if you think about lots of different molecules with different bonds, different atoms, the actual presence of these structures, often they don't occur in different molecules, so they're very sparse, lots of zeros, essentially. So doing some sort of compression thing like this is quite a valid thing to do. Yeah. But this is something that's existed for ages, this sort of fingerprint stuff. Cool. Sorry. It works well for this problem, I would say. I'm going to propose another kernel in a second that we found was a little bit better. But as a baseline, this is incredibly effective. If you think about this, it's very, very high dimensional. Everything's zeros or ones. It seems to do a good job, I think. And also, there's a little bit, when you're doing Bayesian optimization, you're interested in, we'll go into the kind of the motions a bit later on, but you're interested in a model that helps you drive your search strategy. That isn't necessarily the same thing as having a good model, just in general. So often having kind of a simpler model that you can learn quickly, even if it's not that accurate, can be very good for a Bayes op problem, whereas it would be bad for a regression problem. So maybe that's also part of it. Yeah. But another way we might do this as well is using like strings kernels. These are things people are interested in. You can represent molecules in terms of their strings, so the Smile strings. This is a well-established way of representing molecules. And then you can just calculate a kernel or a similarity score based on strings, so something like Hamming distance or anything like that. But you see here, this is the Smile string for a molecule that kind of, at least again with my limited science understanding, looks somewhat similar. And you see that their Smile strings are somewhat similar. And in a Gaussian process defined in this way would reflect that. Cool. But that's not super relevant anyway. I just wanted to have that in there. But this is getting back onto the Bayes op now. Okay. So there's a little bit of maths on this slide, and then we've got more pictures to explain it all again in a second. But let's think about, suppose that I was looking at a candidate molecule. So I've not evaluated this molecule yet, and I want to say, okay, how useful is it? What is the utility of me making a new measurement at this molecule? Okay. So obviously, if I knew the value that it was going to return to me, which I don't at this point, then this would be a very easy thing to define. I'd just be interested in saying, you know, how useful would it be for me to see a measurement of value f? So another important part of this puzzle is this guy, f star. So this would be the score of the best molecule I've seen so far. And obviously that's going to be something that's going to help us decide whether new molecules are worth evaluating or not. Okay? We're always looking for molecules that are going to do better than f star. Yeah. So I've done like 5 steps of my molecule design pipeline. I found a particular good molecule with a particular score. For the remainder of my experimentation, I'm trying to find molecules that actually surpass that score. And one way we might do this, so we have a utility function. So again, supposing I actually know what the objective value will be from evaluating a molecule f, you could write down a utility as this indicator function here. So basically, if I evaluated this molecule and it gave me a better score than my current best one, then I get a 1 for my utility. And if it ends up being the same or worse, I get a 0. Okay? So this is known as just an improvement function here, which is nice. And then another thing we might be interested in is something like how big was the improvement here. So this is saying if I evaluate a new molecule and it's significantly better than my best score so far, I get a very high utility. But if it's the same or worse, then I get no utility. Okay. Yes?
I guess looking at maybe like the next concept, I can assume that the score that you're describing, even though there are multiple vectors, is like a scalar.
At the moment, in the way I've set it up, we're just thinking about scalars, but we're going to get into some multi-objective optimization, which will then go very nicely into the next talk, which is how do you actually model these kind of, I guess, vector output functions. But yeah, good question.
Sorry.
Yeah.
If f is not a function, it's like
This is the point evaluation. Yeah, sorry, maybe I should be more clear about that. Yeah, if we evaluate this molecule, so this would be like f of molecule, essentially. So this is a value. Of course, we don't know what that is, and that's really key, and that's where the Gaussian process is going to come in. But if we suppose that we actually knew what these values would be up front for some reason, then this would be quite a reasonable thing to do. Right. So this is the point. So we don't know what f is, so we don't know what the value will return, but fortunately we can build kind of powerful machine learning models, maybe Gaussian processors, that actually give us a handle on this. So we replace the unknown f with the f that's predicted by my model at the moment, so my Gaussian process model, and then I calculate the expected utility. Okay. So I'm going to integrate over my posterior for f. And yeah, I've got lots of pictures of this in a minute, which will make it clearer. But you're calculating this utility function over the probability that we have from our Gaussian process model. And this is known as an acquisition function. So this is what it looks like. So if we're going to take this improvement idea before, you have this thing called probability of improvement. So now, because we don't know what f is, basically, if you calculate this quantity here, so the expected value of this indicator function, you end up with something that's just saying, what is the probability that this new molecule will give us a score higher than the best one we found so far? And then you can do a similar thing here for expected improvement. So for a particular molecule, this score on the right here will say, how much of an improvement do we expect to see over our current best? Okay? So these are both kind of scores here. The higher the score, the more reasonable it would be for us to do that experiment. Okay. And then this is, yeah, I should have had this right at the top, I guess. But this is f here. So we don't know what f is, but our Gaussian process will give us a posterior, a Gaussian posterior. You've gone through the details of this. There's a special formula, a specific formula for mu and for sigma squared here. But this would correspond to if you have your sausage plots and you were going to slice them vertically. Right? This would be one vertical slice of the sausage plot, just the point-wise distribution at a particular molecule. Okay. So let's go through some of the motions again here. So let's suppose that I have these 3 candidate molecules, and I want to try and decide which one of these I should evaluate. And what I've done is I've plotted the marginal distribution. So again, the slice from the sausage plot for each of these molecules. So what we're saying here is we don't know what the evaluation of this molecule will give me, but my Gaussian process is suggesting it's something that's kind of got a mean around 0 with a certain amount of uncertainty. Okay? And then this molecule here, we're saying we have a good idea that it's quite high, but we have a huge amount of uncertainty. whereas this one's saying we think it's not great, and we're quite confident about that. Okay, so these are different predictions from our model for different molecules. And then F star here would be the best one I've seen so far. And then there'd be a question of, which one of these 3 molecules should I pick based on all of this information? Does anyone want to suggest an option? The last one. It depends if you're maximizing or minimizing, I guess. Yeah. Let's suppose we're maximizing now. The axes, this is the PDF, so this is the probability of, so my Gaussian process model will give me a distribution over what we think the objective value would be at this molecule. So I've sliced the Gaussian process, and this is my posterior. So we get these sort of posteriors for our individual predictions. That's what this is here. That's that Gaussian distribution. So this is the PDF. So we're saying, we really think that the value is here, but we have some uncertainty. Sorry, I can make these labels bigger next time as well. So did someone suggest something? Or? Yeah, why? Yeah, I think that is valid. I think it's possible that you would also go for the first one as well, maybe. It could be that there's a huge amount of uncertainty here. Maybe the expected value is high, but maybe actually if you were going to integrate the mass below, maybe this one is a safer bet. So depending on your sort of risk averse, or you maybe make different decisions, and different acquisition functions would pick different ones. If I was instead going to raise this value a bit, so actually we've seen a really good one so far, clearly this completely rules out this one. There'd be no reason going there. Basically, we're saying the probability that this molecule is better than the one I've seen so far is tiny. But actually, it's kind of also ruling out this first one completely as well at this point. So you very clearly then pick the second one in this context. So that's kind of the cool thing about these acquisition functions, is that they're adaptive to what is the best molecule I've seen so far, and that's going to trade off between exploration and exploitation in your problem. You have this kind of dynamic behavior of the algorithm. Yeah.
Sorry, I didn't really understand why we choose the second. Maybe I don't really understand what the right bet is. Right peak.
Yeah. If you were doing, say, probability of improvement, I guess the probability of seeing an improvement if you evaluate the first one is like 50%. But the probability of seeing an improvement with this one would be much larger than that. If you think about the amount of mass above the best value. Yeah, essentially. So this is the posterior, right? So I'm saying I think that F of this molecule is up here, but then the probability of this molecule being bigger than the value would just be the integral of under this curve above the red line. So let's go through this kind of automatically now. So we have a way of doing this automatically. So we can calculate the acquisition function for each of these molecules, and that will just tell us which one we want to evaluate. And we do it like this, basically. So we'd have some data set, we'd fit a model, and then we'd calculate an acquisition function for each of these molecules, right? So we're going to go through the motions, we'll make predictions from our Gaussian process for each one of these candidate molecules, and then we calculate the acquisition function, and that would give us a number that basically says how good would it be if you evaluated this molecule, okay, based on our understanding now. So then we just calculate that for all of the molecules we're interested in, and then just pick the molecule with the highest score. And I think this is the highest score. Last time I gave this talk, someone kicked off because they kind of got really bored with what I was saying and just went through all of the numbers. But I think this is the highest. I think I did update it, so that's good. Hopefully no one's going to go through that. I'll move on quickly. There we go. So let's go through it more as a sequential process now. So far, we've only been talking about kind of making one set of experiments. So let's suppose we want to start. So we're going to fit a Gaussian process model, okay, to help us drive the search, as we've discussed. And to do that, you need to have like a starting place. So it's very common in this field to have some sort of maybe space-filling design or random strategy to start with, just to collect a bit of data. You can typically, in a scientific problem like this, you can typically do something much more clever than random search. But let's suppose we've just chosen 2 random molecules. We're going to fit our Gaussian process model to these molecules, okay? Use that to calculate an acquisition function. And then we choose our next molecule, this has got a bit out of sync, as the maximizer of the acquisition function, okay? And then you can do a similar thing. So you go back, and we have now more data, so we refit the model to all of the data we have, recalculate our acquisition functions. We'll have a nice picture in a minute of showing you what happens to acquisition functions over time as we collect more data. But critically, it's going to tell us to pick somewhere different. And then you just proceed like that, just one by one or in batches. Does anyone have any questions so far about this setup? Yes.
Sorry, I'm a bit lost in the molecular context. Maybe in a simple term, is the molecule's features or the observation?
Yes. Well, so the molecule is. Yeah, maybe I could be more clear about this as well. But the molecule, that's the input to my model. And then there's a particular property of the molecule that I'm interested in, maybe the stability of the molecule. And that would be the function that I'm interested in.
So each molecule has properties,
Yes.
stability and everything. And for the Bayesian optimization, so you start with like small number of molecules and then you add it
Yes, exactly.
sequentially.
Yeah, and you're trying to find a molecule that scores very highly with respect to the property you're interested in, but with a small number of evaluations, basically. You don't want to have to evaluate all of these molecules. You want to just evaluate a small number of them.
And then you do it in a single model of Gaussian process.
Yes, yeah.
Maybe meta heuristic, usually we have multiple candidates of models and things.
Yeah, I mean, you could do something like that as well. We don't always use Gaussian processes, but I didn't want to say that in this room. But yeah, you can use lots of other types of models here as well. You need something that gives you uncertainty estimates. That's the main thing in order to calculate these acquisition functions. But you can do like ensembles of neural networks, for example, and try and pretend that that's an uncertainty estimate, looking at the variation between them. But I'm going to go through all this again for like a continuous, more standard problem. So this is normally how people introduce this stuff. And maybe this will make more sense. And we can talk a bit more about molecules again afterwards. Okay, so this is a very kind of standard setting here. So this is going to be more similar to the setting we've looked at already with Gaussian processes. So I'm interested here in maximizing a function. Okay, so this is my underlying function. I don't know what this is, like in terms of the experiments I'm going to do now, but this is the ground truth here. And I want to find a very good area of the space. Obviously, there are some like local optima in this problem. So if you were just going to find one of these guys, this wouldn't be great. You want to really find this optima in the middle, so this maxima here, the global maxima. Okay, and you'll see that some other methods aren't good at finding this. But one of the nice things about Bayes opt is that hopefully you've got a good chance of finding this. Okay, so let's suppose that I've collected 1, 2, 3, 4, 5 data points. Okay, so this is all I have at the moment. This is the only information I have about some sort of underlying process. Where would you next make an evaluation given this information here? Yeah. Yeah, we got no idea at all what's going on over here, right? Something crazy could happen. So here we're trying to maximize, right? And it could be that it goes up really high. We don't really know. So that would be more of like an exploration sort of argument there. You'd be saying, right, I don't know what's going on, so I'm going to explore. I think there's also another like interesting place you might go for in here as well. Anybody want to suggest? Yeah.
Between the final 2 points that you observed, since they're the 2 highest ones.
Exactly. So that would be some sort of like exploitation sort of argument. But yeah, you want to kind of trade off these two approaches. But yeah, there's definitely 2 interesting places. So what I've done is I've fit the Gaussian process, and then on the top here to appease Carl-Henric, we have some wiggly lines as well. Sausage plots on the bottom. Yeah, you don't need me to talk about this. But let's go through the motions of this kind of acquisition function that I described before, but this might be a little bit more visual. So we have F star here, which would be my current best solution. So I go for all of the data points I've collected, and that will correspond to this point here, right? So what I'm interested in doing is finding a new point that's going to give me a score higher than F star. Okay? And then on the bottom here, this red curve, that's the acquisition function that I was talking about before. And because we're in 1D, we can just plot it all the way along here. And the way you read this is you look at, okay, suppose I was going to make an evaluation at 0.8. This red line is telling me like how worthwhile it would be to evaluate there. So this is the, is this probability of improvement? Yeah, I think this is probability of improvement. So basically, this red line is just the integral of all of these little red lines, basically. So it's saying, you know, what's the probability that we're going to do better than we've already seen before, okay? So we can calculate this. This is really cheap to calculate, right? We're not evaluating any expensive functions here. This is just, I have to predict from my Gaussian process, and I calculate this utility function. But the nice thing here is that this is doing exactly what we kind of said we wanted to happen. So we said we wanted to make an evaluation out here somewhere. So it's scoring very highly out here. but we also think that this area is reasonable. Okay, so this is very much summarizing the sort of things that we want to see. And then what we can do is use a kind of a standard optimization routine just to find what actually is, across this search space, this input space, what is the best point to evaluate next, okay? And then that would be the point corresponding to the largest acquisition function value. So this is a completely automatic procedure. We're just fitting a model to some data, and then we're calculating the utility function and maximizing the utility function. So there's no human interactions here, but this is exactly the same as what we were doing with the molecules, right? But in this case, we have a continuous input space, so we can kind of plot things nicely. Yeah.
I guess the only thing I'm struggling with here is that the uncertainty drops is obviously very small where you have an observed data point,
Yeah.
but where the highest observed data point is, there's quite a high likelihood that immediately adjacent to that, it's going to be higher.
Yeah.
But it sort of takes a while for the uncertainty to span out, and so there's a kind of conflict there where you've got like a known data point that you know is quite high, but you're going away from that a bit more because you're waiting until you've got a greater uncertainty because that corresponds to where the interval is greater. So I just wondered, is there a way of managing that trade-off?
So I think that's actually a really, really good question. And now that you've said that, I think this is probably expected improvement, I guess, rather than probability of improvement. So this is one type of acquisition function. If you're going to look at the probability of improvement, where all you care about is there improvement or not, then you would end up with kind of large values very close to the data points. And that can be problematic. For a 1D problem like that, that kind of sounds like a good idea. But as soon as if you're in like 5 or 6 dimensions, it means that then you're always just picking points very close to the ones you found, and you never do any exploration. There are lots of heuristics. I mean, the whole field is just a bunch of heuristics, essentially. But there are ways of encouraging a bit more diversity in these things as well. But yeah, that's a really, really excellent question. Yeah.
Right, so back to the point about this, like 1D versus 5D thing. I guess the one you can see like an argmax or that seems to go to like 2, 3, 4D. You can't do that because maybe the grid points to like working out the acquisition function for every point isn't valid. You have to do this with optimization things.
Yeah. Yeah, definitely. And that's kind of, if you're in one of these continuous spaces, you can just use like standard gradient-based optimizers to try and find. There's a whole load of work on like custom optimizers for this problem, because it is quite challenging. Like you always have a very multimodal acquisition function. The only thing it's got going for it is that it's very cheap to evaluate the acquisition function. So you can kind of brute force it. You can do lots of kind of local start optimizations and all this sort of thing.
Do a lot of hosts use like SciPy, minimize, and sort of
Yeah, exactly. So you do like LBFGS from SciPy or something, and you start from lots of different places. You might be a bit clever. You might start them from areas that you have seen that happen to be quite good. It all depends. If you're in very high dimensions, you have to use quite dramatically different algorithms in terms of just trying to find areas that are good. You're willing to be a lot more exploitative in very high dimensions.
Do you have a good way to pick which functions to use? So I know in SciPy minimize you can use LBFGS or you can use NumberMean, or there's a selection of choices. How do you pick between the potential optimizers?
Yeah, I'm not completely sure. Like, it depends on the problem. I've always kind of used LBFGS unless it doesn't work, and then I try other things. And that's a good rule of thumb, I would say, yeah. But for a lot of these problems, so for example, the molecule problem, I was talking about my search space was this discrete set of molecules. You can just enumerate over them, essentially, and pick the best one. In practice, that's not the case. You actually want to design new molecules and things. So in those contexts, you have really weird acquisition optimizers. You might use genetic algorithms that can kind of try and add new bits onto molecules to generate new molecules. And as soon as you go into any kind of non-smooth space, so any non-Euclidean search problem, you end up with like weird acquisition functions and weird things. But yeah, people use lots of different things. If you're doing like a problem where your inputs are, say, binary inputs or discrete inputs, you might use like a linear program or a mixed integer linear programming solution to do the acquisition optimization. There's all manner of different things you can do here. But for these problems, I would use LBFGS, I guess. Yeah, cool. Okay, so let's just go through the motions of this again. So yeah, we have this underlying, annoyingly, I've swapped to minimize here, which is annoying. But so we go down here, and we're trying to find this region. Okay, so we've got these data points. And then what I've done is I've fit my Gaussian process, I've calculated my acquisition function, and then I'm going to find the point that maximizes my acquisition function. So that'll be this guy here. and then I make an evaluation at that point, so that would be this, this green dot up here, and you see that my model has now dramatically changed, right? My model has been updated to include this new data point. So before, when we thought, okay, maybe this region was quite promising, we've now seen that actually it's probably not, right? It's going all the way back up here. So the model's updated, which then also means that the acquisition function is updated, right? We're now no longer interested in this region at the side because the model has changed and it's no longer promising. So that's how these acquisition functions update as well. And related to a question before as well, you see that the acquisition function is always very small around the data points. So for these problems where we've assumed very little observation noise, you never really want to make an observation in the same place. You're not getting any more extra information, right? But for some problems where you might have noisy observations, maybe you would want to make, replicates or things, and you would see that in the acquisition function. So if you've used a Gaussian process surrogate model that had like a high observation noise parameter, these acquisition functions would look quite different. And then we can just kind of proceed as well. So at this point, we've got a good handle of what's going on over here. We kind of think we know where the optima is, the minima is here. So the next best thing to do would be just to really hedge our bets and make sure that we're not missing out anything down here. And that's what the acquisition function is telling us to do, and so on. Okay, so you end up with this sort of distribution of the points. So this is really nice. This is what you want. You're seeing that you're spreading observations kind of quite sparsely throughout the whole of the space, but you're very much focusing evaluations in the promising region. Okay, so this is a very successful run of Bayesian optimization. We can look at another 2D example here as well. So let's suppose that we're interested in maximizing this 6-hump camel function. So if anyone gets into Bayesian optimization or is already into it, you'll find that we have all of these stupidly named like toy problems that bear no resemblance at all to real-world problems, but we're obsessed with basically benchmarking against them. And this is one of those. And it's called that because if you zoom in, it's got these sort of 6 humps. I'm not completely sure who came up with this. But this could be quite a challenging optimization problem for something like gradient descent, right? If you started it off over here, so suppose we're minimizing, if you started your gradient descent off up here, it might get stuck. So that would be maybe an issue here. So I made a GIF here. So on the left, we've got Bayesian optimization. So over time, choosing data points. And you see that it's very much finding these 2 regions in the middle. So it's done kind of a good sparse coverage of the space. But then once it works out these regions are good, it's starting to focus a bit more there. So again, we get a nice efficient coverage of the space. If you use kind of a local method, like gradient descent, for example, you might get some behavior that looks like this. And then you never find the good optima. Okay, so that's kind of another nice aspect about these algorithms, is that they're supposedly quite global optimization routines. And then this is my final kind of example here. You see that this is a problem. So the dark in the background corresponds to very low objective value. So I've run Bayes op for many, many steps here. And you see that we've focused our evaluations on this very, very dark ridge. And then we're a bit more densely packed in the kind of the medium area, and then very sparsely packed in the poor area, right? So again, this has been a very successful optimization routine. You've got very efficient kind of coverage of the space. This was a good way to spend your evaluations, right? Okay. So I've kind of got into this a little bit, but people say this as a statement. So they say Bayesian optimization performs global optimization. This isn't strictly true, I would say. I'd say it's a much more global optimizer than a lot of optimization routines like stochastic gradient descent. But actually, depending exactly how we maximize our acquisition function, depending exactly on what sort of models we use, you aren't guaranteed to always find the best solution. So this is a slightly dangerous statement to make. But on the whole, it is much better for multimodal functions than a lot of optimizers you might see at the moment. The main reason why people are interested in Bayesian optimization is that you need a relatively small number of evaluations, right? Every time I make a measurement of my function, I'm being very clever about where I should go, and so I only need kind of often a very small number of evaluations compared to, say, a brute force approach or a local optimizer. Here are some examples that people have used Bayesian optimization for. So in my old job, I did a lot of this. We were interested in calibrating electric motors in cars. And every time we wanted to try a new car engine, they had to kind of build it and fiddle around with it in the lab, so it was very expensive. So we wanted to find a nice calibration of this engine in a very small number of measurements. And that's kind of the theme throughout all of these. So people also use Bayesian optimization for training large machine learning models. So if you imagine, I have some data, and I want to find a good neural network architecture for this data. Every different neural network architecture I try might take a few hours to train. So I'm only able to try like 20 different architectures how should I very carefully design which architectures I'm going to use? So people use Bayesian optimization in this. This is known as AutoML. We've got the molecule stuff that I've been talking about a lot. And there's this really cool example I found once where people were using Bayesian optimization where it was taking months for them to do an experiment. So basically you'd kind of fit your GP, do some clever stuff, suggest a new wind turbine for them to build. They'd go away, they'd spend a month building it, they'd try it in the field, and then they'd come back and they'd be like, okay, what's the next experiment? So this is a very small number of experiments, right, that you're able to do in this context. But these are the sort of problems that people use Bayesian optimization for. Another point that's maybe slightly subtle is that in any of the slides I've shown so far, we haven't used the gradients of the black box. Right? We can view our objective function as a black box, which means that I can optimize something like a supply chain. Right? I don't need to be able to get gradients of a supply chain or gradients of a molecule, for example. And because we're using a nice statistical model that underpins all of this, we can actually deal with very high levels of observation noise. So observation noise would often cause you issues with kind of standard optimization routines. But because we have this statistical model, we're able to kind of get away with it. Okay, and then in terms of, if you're interested in like specific examples, the first time they built AlphaGo, it didn't perform as well as they wanted to, and there's a really cool paper about how they use Bayesian optimization to fine-tune the architecture, and then they were able to get the model that they wanted. So Bayesian optimization was a very key part of that sort of complicated RL setup they had. Similarly, people have used Bayesian optimization within Amazon Alexa. There's a lot of work on this molecule search stuff. And then more recently as well, people have started to use Bayesian optimization, and I've got another example of this later on as well, to optimize very large, expensive climate models. And there's this really nice book as well. If you're interested in this stuff, you want to know more about the details, I would recommend this book. Does anyone have any questions at this point? Yes, lots of questions. Good. Yep. Yes, please. I've got like, I don't know, 20 slides at the end on this, so if we get to it, then I'll talk about that then. If not, we can chat afterwards. But yeah, it's a good question as well. I do like entropy search, yeah.
About the linear kernel versus the would you say that linear works better because it's a binary input, or is it because it's high dimensional?
The high dimensional, I guess. Like if you're in very, very high dimensions, you're never going to be able to learn, when we plot the RBF kernel, the GP samples you get for an RBF kernel, they're all these cool wiggly functions, right? If you're in very, very high dimensions, then the class of functions you can learn are just crazy flexible. Like you would need loads of data to pin them down. But if you have a linear model in high dimensions, you can kind of learn that without too much data. And as I said earlier, often in these contexts, it's better to have kind of to learn a simple model for the Bayes ops rather than like a really bad, complicated model, essentially. So yeah, you're making your hypothesis class of functions you can learn significantly more simple in a way that means that you can probably pin down what's going on. Yeah. Yeah, not better than if there was no noise, but compared to other optimization routines, I'd say. Like if you were going to use LBFGS and you had noisy observations, it would crash as soon as you got kind of close to a convergent solution due to the way that some of the line search and things are done. There are robust implementations. If you use like the SciPy version, it probably would kind of be okay-ish. But here we're able to kind of acknowledge that our data generation process has noise, right? We have our Gaussian process model. Maybe we have Gaussian noise. Maybe we have other weird sort of noise like T was talking about yesterday. We can directly leverage this in our model, and then when we're making next decisions, we take that information into account. So these, yeah, very robust with respect to noise, I would say. Yeah.
How sensitive is it to like the modeling assumptions we make about the function?
Yeah, very sensitive, I would say. So you have to fit the model. I've spoken already, like it's important to get the right kernel. That's very important. If you think about what the kernel is, that's your prior and what you think is going on. And that's the reason why Bayesian optimization can be very effective, is because you're putting quite strong priors on what you're saying, okay, I'm trying to maximize a function. I don't really know what it is, but I think it's probably smooth. And that corresponds to saying, okay, a GP with an RBF kernel, for example. And by saying smoothness, you're saying, oh, if I see a region that's good, it means there's probably good points around it. And we're able to make all of these arguments. If the function wasn't smooth, then you wouldn't be able to make any of these. If it turns out your function was just a wiggly line, right, you wouldn't be able to optimize it. using this method any faster than just a random search. So the idea here is that, one, we're trying to learn structure, but two, that we're able to inject structure through our prior. Right? And there are lots of problems where you don't have kind of a very smooth function. Maybe you know that you have like a jump in the middle, so there are different ways of including that in a Gaussian process. But yeah, you want to inject as much information as you can. Like, it's a Bayesian method in the end. Yeah.
If you have a function that's sort of piecewise, in the sense that you have like continuous sections of this continuous section, can you model your kernel to account for that?
Yeah, there are ways of like smashing kernels together, essentially. You can have them so they kind of decay out of certain regions, and then a linear combination of them like that. I've seen this done. If you know like where the piecewise bits are and how many of them are, then that's great, and it seems to work quite well. It becomes very problematic if you don't know where the boundaries are, or you don't know how many parts. You have to be very careful there. You have to have quite strong like priors over the number of sections and things.
Could you do something like add a return kernel to a RBF, for example?
Yeah, I mean, that's completely fine, right? You can build kernels like that if you want, but that would give you the same sort of behavior across the whole of the space. So I thought you meant if you had maybe RBF behavior for the first half and then return for the second half. Because you can also do things like that, so like locally active kernels, essentially. Yeah.
Is it possible to make a Bayes-Opt algorithm that does also use gradients if you have?
Yes, yeah, it is. So you can condition, we've said this a couple of times so far this week, but if you have any sort of linear operator of your function, you can kind of condition on that. So things like, if I know the integral of my function, which comes up a lot in kind of physical problems, if you know something about like mass being conserved, you can condition on that. But similarly, also like point-wise gradient evaluation is also a linear operator. So if I happen to know the gradients, then I can encode that. And people do this a lot. It kind of increases the cost of the Bayesian optimization, because you now have essentially twice as many data points. Rather than just having actual data points, you now also have data points and their gradients, and you have to condition on that. But it is an interesting method. And it's quite good as well sometimes for high-dimensional problems. It can help you find good solutions. So yeah, there are many problems. Actually, and with a lot of these climate models now, you can backpropagate through those. So that's a setting where people are interested in. It's not an actual black box function anymore. It's just a very expensive, I guess, white box function. So let's use the gradients as well. They talk about this quite a lot in this book at some point as well, if you are interested in that. Yeah, cool. Yes?
So for Bayesian optimization in the Gaussian process with non-Gaussian likelihoods, do we also, in this case, do we also need to do like some gradient stuff? I mean, to fit the model, do we need to, calculating the gradient, like, do we iteratively, like...
If you want to fit when you fit a Gaussian process model, you do need to calculate gradients of the model. But I guess that's completely independent of the Bayes-Opt stuff, right? That's just, I want to fit a GP with a weird likelihood to some data. Depending on the exact method you use, you typically have to take gradients of the model, but not gradients of the function you're trying to optimize, I guess.
So the fit in the second step in Bayesian optimization really depends on what method, what algorithm that you use inside.
Yes, yeah.
And then after that, you get the model, and then you calculate the acquisition function or something.
Yeah. But you are refitting your model every step, and you use whatever method you need for the model there. But Bayesian optimization with non-Gaussian likelihoods is interesting. You have to do a little bit more of approximations. So like the acquisition function I've spoken about so far, you can calculate those very nicely. If you have a Gaussian posterior, it's great. You might need to be a little bit more careful if you have a Gaussian likelihood. You might need to do some approximations. Yeah, I think so. We've done it for some likelihoods, but not all of them. So I think some of them would be quite hard. Yeah. Yes? Yeah, that's also a good question. There's no, I guess I can't say for all problems. In the ideal setting, if you had a good model, you'd want to update it as much as you can to make it more and more accurate as time goes on. There's a slight issue that typically your model, especially if I'm using like a linear kernel or something, like it's a good model, but it's not amazing. So there's a bit of model misspecification. And in that context, actually fixing the kernel parameters for a few steps might just have a more stable algorithm. You have a bit more time to kind of check your model is doing what you think it's doing, essentially. So yeah, sorry, I don't have a clear answer for that one. But typically, I always refit them at every step. But when things start to go wrong, that's one of the first things I try is I make things a bit more stable by not optimizing quite as much. In terms of the model, yeah, you could do some early stopping, I guess, on that. But when you're fitting these GPs, you're often just using like LBFGS, for example, and that has a stopping criterion. If you're doing like a variational model, some of the like sparse approximations we've discussed, you need to use like a gradient descent method. And then that becomes a bit harder to stop. Yeah.
You would also very often, I don't know if we agree with it, but actually try and integrate them out. Right? You just be less specify quite wide triangles over them, and then you're on a P2 shape on the outside. Because it is very small amount of data.
Yeah, you see that sometimes, but it's hard to do, right? It's very expensive, and yeah, it depends exactly on your setup, but that would be the ideal thing to do. Cool, right, I'll push on and do a bit more. I'm actually, going quite slow, so I'm going to skip over this so we can get into something a bit more interesting. I want to go back to this. So I want to give you a little bit of a flavour of some slightly more advanced things you might do with Basel Ops, just so you know they're out there. Again, talk to me afterwards if you want to know more information, or email me or whatever. But I just want to kind of get you thinking about some of the things that I think are quite interesting in Bayesian optimization. So let's talk now about this batch effect that I described at the start. So far, I've been saying, okay, fit a model, choose a data point, fit a model, choose a data point. But for many problems, I want to say, actually, fit a model, choose 1,000 data points. Fit a model, choose 1,000 data points. So how do I go about doing that? So that's what we do now. Okay. So let's suppose we're back where we were before. We have our Gaussian process model. We have our acquisition function in the red here. So if I had to use this acquisition function to pick 3 points, where would I go, basically? This is another question. Anyone want to suggest? Okay, 2 points. If I had 2 points, where would I go?
The local minimum.
Yeah, so you think, okay, right, it's worth spending some time here, and it's worth spending some time here, right? They're good. What about if I had 3? Yeah.
Another stochastic dynamic programming use of not using stitch. Update the Gaussian process before the
Yeah, so that is a method people use. Yeah. But I guess it's a bit complicated. I'm hoping for something a bit more simple at this point. But what you might start to think about is, maybe I'll have one here, maybe I'll have one here and one here. So I might not actually pick the very best one at this point. What you want to do is spread these resources out. What would be the problem with, so you can't just maximize the acquisition function, say 3 times, right? You get essentially the same point, and that wouldn't be an effective design, right? What's important here is that there's a notion of diversity. So I want to pick 3 points that all score highly with respect to my acquisition function, because they're all points with high utility. But it's very important for me that those points are kind of diverse themselves, okay? So they're spread out, right? So you want to basically spend some time over here and some time over here. If you were going to pick all 3 points to be just here, so spread out a bit there, that wouldn't necessarily be a good strategy, right? They all have very high acquisition values, so they have high utility, but actually evaluating one of those basically tells you about the other 2 as well, so that would be kind of a waste of time. So whatever acquisition function you're going to use here has to have some notion of diversity in it. So that's very important. Okay, so this is where we were before. So we had our acquisition function, so expected improvement. It looks a bit like this. Let's think a little bit about how would you define an acquisition function that basically said, what is the utility of evaluating 2 molecules? Okay? So we need some measure here. And then what we can do is just try all pairs of molecules and then evaluate the pair that has the highest kind of joint utility. Okay? So one thing you might think about doing is just, adding the individual expected improvements for the molecules. But that's a bad idea for what I described before. So what people typically do is this. So this is known as the batch expected improvement. And it looks a bit weird here. But what's happened now is we've gone from a max over, a distribution over just the marginals at 1 candidate point. We now have 2 candidate points, right? So we're interested in what's the joint distribution of these 2 things. We get that from our Gaussian process. And this is what we're calculating here. So now we're interested in the utility of these pair of molecules is measured as how much of an improvement we'll see if we evaluate both of those. Okay? So if we imagine that these molecules are very close together, okay, if they were very close together here and here, that means Fi and Fj would be very, very, very correlated, right? They'd be very similar. So that means that this value max of that and that would essentially be the same as just max of one of these guys. And this is what's giving us the diversity. So if we just leave one of the molecules to target this area and send this one all the way down here, that means that those two predictions are very uncorrelated, or hopefully very softly correlated. So that means actually when this guy is, if this turned out to be terrible, just, if it turned out to be down here, this guy would perhaps be higher up. Okay, so there's this, the total, the expected maximum of these two would be larger than if they were right close together. Okay, yeah.
Is there no expression?
There is not. Well, there is for 2D, this batches of 2. Right? And actually in practice, you don't really use this sort of method because it's very expensive. If you wanted to calculate this sort of thing for like 10 molecules, for example, you'd have to calculate a 10-dimensional CDF of a Gaussian, and it would all get very hairy, and it's kind of a bad idea. So there's lots of other approaches that people use for building batches. But this is quite a nice kind of intuitive way to think about things. People often do like Monte Carlo estimates of these as well, which is seems to be quite effective. So that works. But yeah, you have this nice joint distribution over the Fs. And then it's a case, yeah, if you were going to expand this out to very large batches of 100 or 1,000, some things start to go a bit wrong in terms of the calculation strategies here. So there's a whole kind of host of other interesting algorithms that I can tell you about if you're interested. Okay, and then I'm going to give you a quick flavor now of this multiple object. Sorry, Carl, go on.
Yeah, so here's the question of this. So here, you're not at all using information about how informative J might be for I. Right? So you might, in this case, right, say that I can pick 2 points, but it turns out if I know one of them, I kind of know the other. My model would have nailed that down. Is there a way of thinking about using that as well, like actually using the covariance between I and J?
Yeah, so that is what's happening here. So yeah, you're saying we actually have this joint distribution for Fi and Fj, right? So there is a covariance structure here. Calculating this guy, you have to. This is a non-linear relationship of the two different things, an expected value of that. The covariance is going to come up in the calculation here. Like that's very important, right? Like if they were perfectly correlated, then it's basically the same as just having one of these guys, and then yeah. So that comes in, and that's why this is expensive for large batches.
So what does that max actually mean, right? Does that max return one value?
Yes, yeah. The max of those 3 things.
Okay. I'll have to ask you about that later.
Yeah. But I mean, this is batch expected improvement. In 2D, you can kind of calculate it. Higher dimensions, it becomes very challenging. But it does. This is exactly the thing you want to be doing, I think. But in practice, it's hard. So there's lots of other heuristics you might use that scale much more nicely, like Thompson sampling and batch penalization and things. Yeah. Cool. And then let me just think a little bit about a slightly different problem here. So this is how I motivated this at the start. I said, actually, typically, I'm interested in multiple objectives, right? I want to find a molecule that's good for, it's very stable and it bonds nicely to a target. So let's suppose I have 2 objectives here, F1 and F2, and I'm interested in finding a molecule that kind of does well with respect to both of those. Okay. So that's kind of quite a poorly defined problem, and people don't, it's quite difficult to kind of formulate this mathematically, but this is the way that people do it. So this is a very different plot to the ones I'm showing you so far. This is a plot of, I've got loads of different molecules, and I've plotted on this plot exactly where they sit with respect to their F2 score, so their second objective, and their first objective, okay? So this is a minimization problem now. So for example, I'm interested in finding molecules that have got small f1 and small f2. Okay, so which one of these molecules is the best molecule? Yeah.
What's the 6 closest to the 3 difference?
Yeah, exactly. So you know the answer already. But if you didn't know the answer, you'd kind of say, okay, maybe this one is good because it's low with respect to both of these metrics, right? But actually, this one here is even better with respect to this one, but it's worse with respect to this one, right? So there's a whole spectrum of kind of good molecules in this space. There's no single unique best molecule in this setting, right? There's kind of a trade-off. What is clear is that this molecule is trash, right? It's possible to get molecules that are better with respect to F1 and better with respect to F2. So that's clearly a terrible molecule that we don't want to consider. So that one, we would say that one is dominated by, for example, this one here. So this one is better with respect to both objectives than that one, right? However, this one is not better with respect to both objectives to that one. But it's very unclear exactly which one of these molecules are better. Certainly for someone like me, for the actual scientists that we pass this stuff on to, they can start to make principled decisions about this. But at this point in the game, if I just know I'm interested in these two objectives, there's kind of a whole spectrum of solutions that I might be interested in. Yeah, somebody had a question? Yeah.
So do we not know the weight of our different objectives?
Yes. I struggle a little bit with that. So that's the way that people try and deal with this problem, is they say, actually, I've got a single objective, which is 5 times F1 plus 2 times F2. All right, and you could just optimize that and find, but it's very, very hard. If you talk to a scientist or someone in industry and say, which objective is it 5 times more important than F? It's very hard to get these numbers out, and it's often very problematic, I would say. You might run an optimization routine with this weighting, and then the solution they get, they're not happy with. So I do like the idea of this Pareto front stuff, which I'm coming to now. Was there another question somewhere? No, cool, okay. So we have this thing called the Pareto front. Okay, so this is going to be basically the line that connects all of the points that aren't dominated by any of the other points. Okay, so this point here, this was dominated by this point, for example, and just that point. But this one here, there is no other molecule that's better on both counts, right, than this molecule. There is one this molecule here is better with respect to F2, but it's worse with respect to F1, right? So this is kind of the spectrum of solutions that we might be interested in, depending exactly on the sort of relative trade-offs the scientists might make between the objectives. So this is the set of kind of optimal trade-offs, it's called, or the Pareto front, okay, this red line here. And then using that information, we can now start to kind of build an acquisition function which is going to help us basically pin down this Pareto front. So the ideal scenario would be to find loads of molecules kind of out here somewhere, right? We want to make this Pareto front to be as big as we can and as close to the origin as we can, because these are the really good molecules, right? Ones that are very low with respect to both objectives. So one thing we might think about doing is collecting more experiments that allow us to move this red line towards the origin. Okay? And that's actually the motivation behind the acquisition function we'll use here. So here we're interested in what is the utility of evaluating a particular molecule if we suppose that it was going to return a particular F1 value and a particular F2 value. Okay? Of course, we don't know what F1 and F2 are, so we use the Gaussian process model and that sort of thing. But let's just look at the utility function first. So if we suppose that the molecule we're going to evaluate actually had this value, so F2 and F1, so it would lie about here, we could look at, okay, what's the difference between the new Pareto front that we calculate with this new molecule? So this molecule now dominates this guy and this guy, so we're no longer interested in them, so we lose them from the Pareto front. And you see that the Pareto front's getting closer to the origin. So what we could do is measure the volume improvement here. So how much of an improvement in volume is there in the Pareto front? So this is called the hypervolume improvement, and this is the utility function people use in this context. So you kind of add up all of the volume in there. If this molecule was going to be out here, so this turns out it's not actually useful, we've got no more information about the Pareto front, we've not found a better solution kind of with respect to any metric, so this leads to no improvement. And then if we had a guy down here, you see that we get a nice big improvement here as well. Okay. But of course, we don't know what F1 and F2 are, so we just kind of get them from our Gaussian process models. So we might have one model for one of the objectives, one model for the other objectives. In the next talk, you'll hear about how you could actually model these two things together and get a more powerful model doing that as well. But you calculate this guy, this utility function, the expected value of this utility function over your model. And then there's all kind of extensions if you want to do batches with multi-objective, this sort of stuff. There are some problems here in terms of the dimensions, so the number of objectives you might be interested in. Okay, so the first thing you do, if you go to someone in industry and you say, okay, I'll help you solve your optimization problem, they go, okay, I've got 10 objectives, right? And then basically all the calculations here become absolutely terrible. It becomes very difficult to calculate anything. And you have to ask them, why do you want to, what would you do? If I could give you a 10-dimensional Pareto front, like, they wouldn't even know what to do with it. And the maths wouldn't work. You can't calculate these things comfortably in more than, say, 2 or 3 objectives. So kind of an art of like being a practicing Bayesian optimization person is trying to argue with people and convince them that some of their objectives are constraints, for example. So here we might be saying, actually, the problem they really care about is they want to find a molecule with very low F2, but that has an F1 less than 5, for example. And that's a problem that's much, much, much more easy to deal with in a Bayesian optimization setting. But for settings where you really, truly have multiple objectives, this is a good approach. Yeah, do people have questions? We could just spend 5 minutes on questions, or I can go into this, but this is a whole can of worms. But someone did ask for it. Yeah, okay. I'll do a bit of this, and then we'll stop. But we've spoken a lot about expected improvement. So this is a very nice way to do Bayesian optimization. It's one way of measuring kind of and balancing exploration and exploitation. But you might do something different. You might do something called entropy search. So this is something that I'm quite interested in. And there are lots of acquisition functions out here for like multi-objective versions of this, batch versions of this. It's a very principled way for designing experiments. So it's kind of one step up the ladder in terms of Bayesian optimization complexity. I don't need to do the recap. We're good on this. But let's think a little bit about if I have a model, so this model here, this orange model, okay? And I've got these crosses, these are my data points. Let's think for a moment, what is this model telling us about the distribution of X star here? So X star is the maximum, I guess, for this problem. So there's no closed form expression for like the maximum of a Gaussian process. But what we could do is build it up by a sample. So this is quite interesting. So here I've got this green line here is a sample from the Gaussian process. And I could just write down, OK, what's the maximum of that sample? And I could do the same thing for many samples. And over time now, I'm building kind of a histogram of the distribution of the maximum value according to that Gaussian process. Okay. So this is a terrible, gross, sort of horrible distribution, right? Very multimodal, looks very weird. And it's kind of interesting. You started from what is a very simple Gaussian process, only 5 data points. But actually, the information that this is telling us about where the minimum is this horrible wiggly function, right? And I think this is quite interesting, that such a simple model here actually kind of induces this distribution over X star. Okay. But this is what it's telling us. So this is expected improvement, which is what we've talked about already. And what this does is it's making a calculation that only needs your marginal distribution, right? If I want to say, what's the utility of evaluating a particular molecule, all I need to know is what does my model predict at that molecule. So it's not using full information about X star D, right? So this distribution here, so this is the full information I have about where my maximum might be. So there should be a way of kind of being more clever about what you're doing, like taking in all of the information, so using the fact that you've got this joint model over your outputs, over your data points, sorry. And it turns out you can. So there are strategies here that actually try and reduce our uncertainty in this distribution, right? If we reduce our uncertainty, so if we collect more and more data points to whittle away our uncertainty, so reduce some of this blue guy here, make it more narrow, we're obviously going to, over time, really focus in on a model that's giving us a single estimate for the maximum value. Okay, so that's quite a natural strategy to take. It's quite interesting to think a little bit about how you should measure uncertainty in this context. So people often use variance to measure uncertainty, but differential entropy is what we're going to use here. So have people come across this before? Many people? I guess physicists have. Yeah, not so many. So this is another way of measuring uncertainty, inspired by a lot of kind of physics stuff. And this is interesting. So here we're interested just in what are the deviations in my probability, basically, how much variability there is. This is looking directly at the mass function of the distribution. So px here would be the PDF of my distribution. And we're interested in basically how big is that. So if there's lots of mass, like lots of locations in my search space that have quite high probabilities, then this would be quite high. I can show you this in terms of pictures. I'll ignore that for now. So in terms of entropy, so here I've got 3 different distributions, and I'm going to calculate this guy here, this differential entropy. And you see that if you have a Gaussian distribution, you have certain entropy. If you had this normal mixture here, so you've got 2 modes, there would be a certain amount of entropy, measuring how much uncertainty you have. But actually, if you were going to send these guys really, really far apart, in terms of the definition of different entropy, that would have the same amount of uncertainty as this guy here, right? Which is quite a natural way to think about this. But if you were going to do instead variance here, right, the variance of this is dramatically larger than the variance of this one. Okay? So variance can be quite a problematic way of measuring uncertainty for multimodal distributions. And so it's kind of difficult to use that in the context of Bayesian optimization. So if we're interested in like doing stuff with weird distributions that look like this blue one, right, it becomes quite difficult to start to use variance as a way of reducing uncertainty. It's much more natural to think about differential entropy. And that's exactly what entropy search does. So this is how we do. So we say, OK, we're going to make our next observation so that we reduce our uncertainty in this distribution. So we try and say, OK, let's reduce our uncertainty about where the maximum value is. And we measure this in terms of the differential entropy. And we define our acquisition function as the points now. So we're going to pick points that give us a large expected reduction in entropy. OK, so we say, how much entropy is there already in the system? And then how much entropy would be left after I make this new evaluation? And then clearly, if we kind of maximize this over x, we find the point that's going to give us the greatest reduction in uncertainty about x star. This is, in practice, fiendishly difficult to calculate, but there's lots of interesting work, people calculating these in different ways, so these different terms in here. And this is a very, very large area of research in Bayesian optimization. People are coming up with lots of different methods here. But it's a very principled way of dealing with things. And it becomes quite nice. If you've got like a new problem, maybe there's like a multi-objective part and a batch part, you can typically kind of write down what this would look like, whereas it's quite hard to come up with new expected improvement-based methods to a customer problem. But it's very easy to think about, yeah, I'm just going to make my next measurement that reduces the uncertainty in the thing I'm interested in. That's a very natural way to think about things. And it means that you can do a lot more maths for these sort of, if that's what you're interested in, you can prove a lot more things for these sort of methods as well. I'm going to stop there. I think it gets into a load of weeds after this, and I don't have enough time to go through it, so we'll leave it at that. Cheers.
Fantastic. Maybe we've got time for a few questions, because Poppy's not ready yet, I think. Yeah. Do you have a question? Thank you, Andrew.
Yes.
I've been musing over this a little bit, but I think I missed a link between, like, at the beginning with the molecular design example, we talked about that the primary thing that the GP is interested in is the difference between two molecules, right?
Yeah.
Not necessarily, but wouldn't that difference still depend on how accurately your inputs describe the molecular features?
Yeah, definitely. Yeah.
Okay, so then how does I guess just how much emphasis needs to be put on selecting the correct features for your molecule or whatever your thing was versus selecting the right kernel for those features?
Yeah, I kind of view them as the same problem, like because typically you might use one featureization in the molecule, and then there'd be a particular kernel that works well with that. So typically you're kind of going through like pairs of kernels and representations. Like you might use small strings, selfie strings, fingerprints, fragments, any of these things. Lots of different descriptors, all are kind of taking into account different sort of bits of scientific knowledge people have about the problem. Like, and you would often try lots of these different things. You could do some sort of model selection, perhaps, where you see. There are methods as well that are purely data-driven, so a lot of neural network-based approaches. A lot of the work I do, I use variational autoencoders to kind of learn representations from molecules and in a data sort of driven way. But that becomes quite complicated, and you need to be in a problem where you've got huge amounts of data for that to be feasible. But for these problems that I've kind of motivated, where you've got small, if it's like someone in a lab, a small lab, and they're going to make 50 molecules in batches of 10 or whatever, yeah, you need to kind of have a representation up front, essentially. You're not going to be able to learn that from the data. But it's good, yeah, you need to have the right representation. There are lots of interesting papers where people have like compared complicated neural network approaches with like simple GPs with the right kernel. And if you get the right kernel for the problem, if you try a few different kernels, then you can absolutely smash them often. Yeah, it's all about getting the right kernel, and that can be challenging, I would say. Yeah.
Thank you very
Yeah, so I mean, RBFs, it's not necessarily a problem with the RBF as such. It's when you fit it, it's very prone to overfitting. So if you kind of constrain the length scales to be very large, for example, there's some interesting work recently where they put quite strong priors on the length scales to make sure they don't overfit, and that can work very well. Additive models are a thing that I'm really into these days. So where you have, you assume that the function you're trying to model is actually a sum of independent functions, each of which take in just a small selection of the inputs. So you're effectively breaking down what would be a very high dimensional problem into kind of a sum of smaller dimensional problems. And for many problems, either that's just a good first approximation, good enough to do Bayes opt, or you actually know something like maybe I'm fine-tuning my climate model that comes with different parts, like different systems. I might have an atmosphere model, an ocean model. So actually it makes sense that my objective function somehow, like the inputs corresponding to the ocean model might all play together, and then the inputs corresponding to the atmospheric model might all play together. So you can actually partition it up and break down the problem like that. And there's some nice methods in the GP world to calculate those models very efficiently. So if you look at like additive Gaussian processes, for example.
Yeah, so this is like entropy search. So it's really less the difference of your current data, like the emission as I understand, this is only useful if you have more, if you sample more than one point type. Because, or if you only will sample one point, then you could just calculate the entropy and take the one with the largest entropy. But here, when you sample Y, application X, it's like you calculate the combined.
So for these problems where we're doing like maximization, like you have to take into account entropy. The entropy is in the output value, right? And then the way that kind of comes through the maths is often it's corresponding to some input deviations as well. It's quite a subtle point there. If you're doing like an entropy-based method just for active learning, then you don't necessarily care. You can just do entropy in terms of the values themselves. But for this context where you're doing optimization, everything becomes a little bit more complicated. Because you're not just interested in reducing uncertainty, like total uncertainty. You're interested in reducing uncertainty about, say, the maximum value of the process. And it becomes a little bit more fiddly. We can talk about this afterwards, if you like. Yeah. Yeah.
So your choice of terminal has a big impact on the shapes that you can factor out with some of the squiggles, right?
Yeah, yeah.
Does that then have a big impact on the types of acquisition functions and optimizations you can use? Because like, I guess I'm trying to understand do the acquisition functions and the optimizations kind of assume some kind of pattern in these squiggles to do their work, or kind of all.
I guess you're normally just pulling in like general purpose optimizers from SciPy or whatever. You could imagine like having strategies that were a bit more custom. Like if you knew you had a crazy small length scale, so you knew the function was very wiggly, maybe you do more like local restarts and things like this, I guess. But typically it's kind of I guess just standard pulling that in. Yeah, I mean the acquisition optimization is a real kind of art, I would say, for any sort of really interesting problems. That's the hardest bit of the whole process, I would say.
I think you can nearly say that, like, if you have no model mismatch, it doesn't matter what acquisition function you're going to use, you're going to find it. You always have. So therefore, you try and hack the model mismatch by picking an acquisition that use case data points, so that you don't have a model mismatch with those data points, because then you're okay, right? If I go function that's super wiggly here and not wiggly here, but if the length scale is this way, right, as long as my acquisition don't go in here, I'm okay, right? So I'm still going to find the mismatch, which means they are super connected.
Yeah, it's all a bit of a dark art, really. It's a load of heuristics, this, I think, but it's very powerful. I think I disagree as well. A bit more of a philosophical comment on calling it Bayesian optimization, but unfortunately that's what it's called. I think like calling it optimization suggests that you're guaranteed to optimize something. I think it's much more like Bayesian search, which is unfortunately what people call the thing I started. But if that didn't exist, I think that would be a very nice name for this sort of work. The idea is, we've got some system, we have a very limited bandwidth for more experimentation. We just want to find something that's hopefully better than what we have. This is a really nice way to do that. You're not necessarily guaranteed any notion of optimization per se. So it's been a bit misleading when I've worked with people in industry and we said, we're using Bayesian optimization. They say, how do you know this is the optima? And I say, I don't. And that's quite difficult sometimes. But I think some sort of Bayesian search is a better way to think about this problem, these methods. Yeah.
Fantastic. So let's
Cool. Yeah.
can